dimension of the microstrip line. Microstrip line is this is physical. It's a cross section of the microstrip line. If you want to calculate your VP and your Z0, your characteristic impedance, you will need to know your thickness and the width of your transmission line, and also what is the dielectric. What is the dielectric? The constant epsilon r for this microstrip line. From here, I will give you something extra. Okay, I'll give you more opportunity to ask students. Okay, who haven't, can you raise your hand? Who haven't write yet? 你的啊？答对了吗 ？No. Raise your hand. You haven't get the right answer yet. 1, 2, 3, 4, 5. Okay. 5层。Okay. Okay. I have a machine called VMA. I measure I put a microstrip line on it. Okay, then I can measure the phase theta from VMA. Okay, so what is theta? If I measure the phase of a line, actually because the theta depending on how long the line is, okay? How long the line is, not in this direction, it should be in this direction. If I measure theta, what did I measure? The phase. This is a cross section, and I want to see this is a cross view, the side view. This is a side view. I look at from the side. You will have a side here. But this is ground, but this is from the side. This is only a little bit. Okay? And this is the physical length L. When I measure the line from here to here, I measure theta. What exactly did you measure? Can you tell me? Theta equals to any of you haven't get the right answer yet? Youyu, do you want to answer a question? Theta equals to? I don't know. No? Huh? Okay. Beta. What? Theta equals to? Yes. Okay, you got the right answer. Good. Okay. If I measure two different microstrip line, I measure this one. This is a DUT1, and I measure DUT2. They have different L1, and L2. Okay, I measure different lengths of that. So I measure L1. I measure beta L of that. I got theta 1. And I measure another sample with different physical lengths. I got theta 2 for that. Okay? Let me write more clearly. So I measure theta 1 and theta 2. Okay? Theta is what I can measure. L is what I can fabricate physically. Okay? Understand this? You understand this? How we set up? So, if I obtain theta 2 and theta 1, and I do some calculation, delta theta equals to delta theta 2 minus delta theta 1. Can I do that? Yes. I measure I measure 2 theta. So I do the math. I do the calculation. I measure phase of this line. I measure phase for another line. So the difference between these two phases is delta theta. So what can I change this equation to? Delta theta equals to what? You want to answer? Okay. Delta. Beta. Yes. Okay, good. Got the right answer. Everyone happy? Okay. Right? From let's copy delta theta equals to beta delta L, right? So if I transfer the beta, I use this one. Beta equals to square root of epsilon E over C from here. And omega. Sorry, I'm lazy. Let me write more clearly. From this equation, what can we do? What can we have? Beta equals to, who else? Help me. I already write down. Okay, come here. Help me to write down beta equals to from that equation. Okay, can you put beta inside and write down the answer here? One more help. No, not yet. Solve the equation for epsilon E, please. Can you do that? Yes, I think you can do that. Everyone can do that, right? Okay, let me do something easier. Do this one first. Okay, you find a square root. Are you sure? Delta is here. Yeah, that's what it is. calculation. We do it right, do it slow. We need a right answer. Okay? Don't hurry. I want a right answer, correct answer. We can always wait. So what is epsilon E? Good. One of you want to answer my question. I want you to tell me. Okay.
That's square.
Huh?
Square of
Not square root. Not square root.
Uh-oh. Too nervous, huh? Too nervous. Right? Too nervous. Okay. Answer me a question. What we do now? What did we do at the beginning? We measure different lengths of the strip line, right? What did you measure at the beginning? How? Tell me, what is this one? Okay, you just tell me what is.
Okay.
Let's go back to beginning. What is delta theta and delta L? What is these two? What are they? Okay. Huh? What is delta theta? Okay, let me give you an answer quickly. Okay. You got this final answer, this final equation. What we can do for this one? I measure two samples with different physical lengths. So I know at the beginning, I measure, so I made two samples with different lengths. Okay, so I know this number. Okay, I know these two samples, the length difference about these two samples. Okay, and I measure the phase of these two samples. This is measured and calculated. I use VNA to measure the phase of first sample. I measure the phase of second sample, right? And I do the math, I subtract. I get a difference of these two samples. So I measure delta theta. I have delta L. C is the speed of light. Omega is the frequency I just give you, I ask the frequency. So I measure this one, I know this one, I know this one, and I know this one. Then I will know the effective dielectric constant can be measured. This is a very fundamental method to measure epsilon E of the microstrip line. This is about the measurement. Okay. What is the epsilon E? I can measure the phase two samples and I put them in the equation, and I know the epsilon E. Okay? Because you guys didn't move, and this is how we measure epsilon E. Okay? Not so hard, right? What you need to do is you measure two samples and you obtain two phase and you do the subtraction. That's it. Put that in the equation. You know epsilon E of the microstrip line. That's not epsilon R, it's epsilon E. Okay? Okay, we can do some exercise if we have a lab class later. Yeah, I think Pengha already took it, right? And Abi already took it. That's what we did, remember? This is what we do. The same question, the same equation. And who else already took the class yet? Okay, that is what we do in the class. Because too many maths, we need the computer. In the class, I explain the equation. Maybe you didn't get it when last semester. I show Guo Rui show you this equation. You feel it's too hard, but it's time for you to understand. It's not so hard, right? We derive it step by step by ourselves. Hard? No. Easy. Okay? So, I already finished everything important I need to explain carefully about a microstrip line. We can see the slide for more math. So far, we are talking about something more, I think the concept, important concept. But others, you just remember you have a book you can refer to. You have PowerPoint you can refer to. Those are just only equations, okay? Turn off the light for me, please. Okay. So microstrip line, geometry, the same again. Most of you are familiar with. The reason why this is quasi-TEM mode is because if that is a coaxial cable, all the EM waves are covered inside the conductor. But for the microstrip line, it is not possible because your waves are leaking outside in the air, okay? So you need to use the epsilon E instead of epsilon R because of the leakage. Your EM waves are leaking in the air and also in the material. Not everything is in the material. If everything is in the dielectric, so it is a TEM mode. Some part of it is leaking outside. So we can only use the quasi-TEM mode, okay? This is about the E field, electric field, and the dashed line, it is a magnetic field. Not only electric field, but also magnetic fields, they are leaking outside the material. So that's why we need to use the numerical solution. Those are very ugly comparing to TEM mode. You will see huge equations. Those are obtained by some scientists. Okay? So I already introduced this one, so you should understand that. This is what I did. What I did already. So, okay, now the equation, don't be afraid. If you have epsilon r, you have the dielectric constant epsilon r. What is the epsilon E? By using your equation, you will use not only epsilon r, but also you need to know the geometry of your microstrip line. You need the ratio between, D is, I'm sorry, use D. So D is H, D is the thickness. D is the thickness, and the W is the width. I use H there, right? But it's actually D. The thickness is D. So you will need the ratio of your width and the thickness, and then you will have epsilon r, and then you obtain your epsilon E. Looks a little bit different, but the same is the same parameter. Epsilon E, you will use this one. Okay? Ugly equation, but just the equation. You not only use epsilon r, but also you need a dimension, the geometry of your microstrip line. Put the numbers in. Actually, you need a ratio. Okay? For epsilon E, no problem, right? So after you obtain your epsilon E, then you can get beta and the VP. Everything will be the same except epsilon E. Okay? And also except Z0. Z0 has another equation. Not only this one, this is for coaxial. For epsilon E, anyone have a question? You just copy this equation and put them here. Everything is the same for this part, for your beta, for your VP. Okay? For microstrip line. That's why I say the beta of coaxial cable and the beta for the microstrip line are different, because for coaxial cable you use epsilon r, for microstrip line you use epsilon E, and then the microstrip line, your epsilon E is relevant to the geometry, not also the material. Understand? You can imagine that. You can imagine that because you have wave leaking outside, so your geometry is also important, not only the material. The geometry is, if you're leaking, is different. That's why epsilon E is different. Okay? Epsilon E is relevant to the geometry, not only the material. That's why you use an effective dielectric constant. This is the most important part of our microstrip transmission line. Don't be afraid by the ugly equation, just the equation, put a number in, give me a right answer, okay? If I ask you a question about that, I will give you a geometry. Do you use your calculator? Give me epsilon E. Okay? Just the skill of calculators, using calculators. For the characteristic impedance, still have very ugly form. For coaxial cable, it's this one. But for the microstrip line, scientists obtain the answer, the equation for characteristic impedance due to some numerical method. Okay? There's no way to explain. This is just the equation. if you have the geometry, you have epsilon E when your geometry, your width over D, the ratio of W over D is less than 1. You use the first equation to get Z0. Okay? If your W over D is larger than 1, it's a wider width. The width is very wide compared to the thickness. You use another equation. Okay? Also, first you need to obtain the epsilon E at the beginning. You put the geometry, you put epsilon E. Because for this equation, you usually know your geometry at the beginning, so you can choose which equation you will use at the beginning. Because you know W, you know D, right? So you need to decide which equation you are going to use. Understand? After you know that, you just find one. Don't worry about that. No one can remember these equations. This is one of the reasons why it is an open book final exam, right? You need to find out the answer, copy the equation, put a number in, and give me the Z0. If I give you epsilon R, I give you epsilon R, you need to obtain your epsilon E by using the equation of epsilon E for the last page. After that, you calculate Z0. Okay? Then you can do everything we did in chapter 2. We also connect everything to each other. Remember, for the question I asked you for a coaxial cable, happened again for a microstrip line. Except the equations are extremely huge. Okay? You use the geometry to obtain Z0. You use the geometry to obtain the beta. Then you can do all the equations of what we asked in chapter 2. Again, but different types of the high frequency transmission line. Are we good? Okay. I don't need to explain, they are numerical results. Actually, many of the microstrip line equations are derived in CU Boulder, the school I got PhD, and the professor was the advisor of the professor when I started my bachelor degree in NCKU 成功大学 My bachelor degree 大学是在成功成大念的 Okay. The professor, he was also graduate from CU Boulder. His advisor is Casey Gupta. You can find out his name when you are doing a lot of microstrip line. So those equations, many of the equations of the microstrip lines was derived, obtained from the teacher of my teacher. Actually, so they are derived by the teacher of your teacher's teacher, the teacher. Okay. Okay. Yeah, it is. The CU Boulder is a school. We have very key result about the microwave engineering. That's why I studied here. You can find out maybe you can check your book about the part of microstrip line. You can see Casey Gupta. He is already passed away. Yeah, the teacher of my teacher. Okay, those those equations, the numerical result, okay? It's not, I think the most difficult part is on the whiteboard. They are just equations, just put a number in, get a number out. This is not the hard part, okay? It just takes time. And to explain why it's more hard, this is logic. This is no logic. You just put a number, you got Z0. Okay. Because of these two equations, they are the numerical result. So it is not easy to obtain the reverse equations. You can also get a reverse equation by also the numerical method. What is the reverse equation? The reverse equation is like, how can we obtain 15 ohm? You know, the question and the answer is upside down. So, what is the ratio of W over D for 75 ohm? And then get a numerical solution about the reverse equation of the characteristic impedance versus the geometry. For this one, you will need the A and the M because they are too complicated. That's why we usually, this is the method we try to reduce the size of the equation because the equation is too huge. It's very difficult to write down in the book or write down in one-page paper. So they take a similar term outside. For this term is A, for this term is B. For you guys, you want to use this equation, you put for this one, remember this is epsilon r, this is not epsilon e, okay? You put a number epsilon r in, you put a Z0, you want to obtain the characteristic impedance, and then you obtain A and B. Of course, you don't know the answer is less than 2 or larger than 2. For this one, maybe you need to try. Okay? So whatever, this is a reversed equation from last page. Okay? From WD and epsilon E to obtain Z0, and this one is, you have Z0, you have epsilon R. What is the ratio of your geometry? They are very similar, but obtain this one from a numerical method. Okay? Are we good here? And I think everyone is very lucky because all of you, most of you, except you have an ADS, right? But you also have a website. You can use a website to key in the microstrip calculator. You just input the numbers in, they will tell you what is Z0 outside. But I'm just telling you what are those equations. And those are the equations they are using in the POSA. Okay? Okay? Sure.
W by D in this page is less than 2.
Yes.
And the last page is less than 1.
Yes.
So it's two different.
I don't know why. But I know how to use it, right? That's what we do now. But maybe somewhere they maybe have some explanation. That's a good question. I noticed that, but I don't know the reason. But it doesn't bother to use it. They have some, I think maybe some reason. I don't know. Maybe in the book, maybe I just miss it. Yeah, you guys have this chapter, right? They have the same equation, right? Do you? Check your book. This is the thing we do. This is in chapter 3, the middle part of the microstrip line, right? The same equation. This is how we calculate the characteristic impedance and the beta by using epsilon E first. you need find epsilon E. Those are very important. You see only epsilon E. Yeah, you find epsilon E, you got a beta, and then you use the equation to get it easier. And most of you, I don't think any of you will calculate by yourself, except me or in my class. I will try to push you to use MATLAB to key in those equations to find the answer. Try to compare the result with your result of the ADS or AWR or any other calculator. They are supposed to be very close. I didn't say the same. They should be close, but sometimes they choose different functions, different equations. There is, because if you listen carefully, you remember that I told you this is a numerical result, right? That's why you don't have only the single answer. You don't have the easy answer. This is the numerical result. So maybe use different method, have different accuracy. The equations is different. And you will have close result, but not the same. Okay? There is no single, we will call it, how to say that? Synthesis result. There's no synthesis result. We have only numerical result. Okay? You solve, you use some curve fitting technique. You fit the measurement result to find out, okay, maybe it looks like this one. Okay? Okay. So far, I think maybe you can follow. But there are some expansion for more professional students or professional engineers to understand these equations. For the epsilon E, for the equations we used here for the epsilon E, it is only the effective dielectric for very low frequency. I'm telling you that so far what you learn is very simple. In the real world, this is just a simple case. In the real world, your epsilon E is supposed to changing depending on the frequency. If you put epsilon R in there, if you key in your epsilon R, it is a constant. If you think like this way. If your epsilon R is just a constant, like 4.2, your geometry is keeping the same, right? So your epsilon E is a constant. But when you measure by using this method, you will realize that your epsilon E is changing according to your frequency, right? Because your delta theta is changing depending on frequency. How do you explain this one? By this equation. Because it is not accurate yet. The equation only tells you the epsilon E of low frequency. This is where you put the frequency here. Okay? For the real world, your epsilon E is changing by different frequency. So, I will give you, Toza gave you another equation of epsilon E. More accurate epsilon E changing according frequency. I will not ask you by this one, it's too much. But I need to tell you the truth. What you learned so far is just not enough. Okay? Your epsilon E, depending on frequency, is the epsilon R minus epsilon E of the epsilon E equation over 1 plus the function of g. The function of g is a frequency-dependent function. What is function of g? There are many different functions of g by different scientists and different papers of the function of g. The function of g in your POSA, it gives you that it is a function of small g squared, and the small g is 0.6 plus something relevant to your characteristic impedance, or you realize that something, when you want to obtain epsilon E, and you need to know Z0 at the beginning. Is that upside down? A little bit weird, right? Okay, but whatever, this is the equation given. And there is another FP, and the FP is another equation relevant to Z0 over 8 pi multiplied D, the thickness. Okay, you put everything in, and then you have parameter frequency, and you have the capital G function, then you will obtain another, it is a more general and more accurate frequency dependent effective dielectric constant. And more complicated. Okay, this is more professional to find your epsilon E. Okay? I obtained this one from your book, from POSA. I think you also have this equation as well. Okay. And another part, this is how we obtain, how we measure epsilon E. You can calculate that. You can measure it by using the different phase we introduced at the beginning, right? Okay, this is how we obtain that. You have, once you have C, you have omega, and then you can measure epsilon E by this equation. Okay, we can have fun if you take a lab class later in other semester. You can have fun of this equation. But I think for next semester, I don't have this class. Maybe 1 year later or maybe 2 years later, if you are still here. Maybe. Okay. Okay. And the last page is when you measure epsilon E, how to obtain epsilon R. At the beginning, you can see that it is, you have epsilon R, you have geometry, you have epsilon E for a low frequency, right? And after you use the equation of capital G with capital G here, you have something very complicated, epsilon E. But sometimes, the sometimes is what I said, sometimes it means, if I use this equation to measure epsilon E, right? For most of you, you will ask the question, hey, teacher, what is the epsilon R if we decide a circuit? How do you think about epsilon R? 4.2 or 4.3? Which one is correct? I will tell you that go to measure epsilon E first. Right? You can do, you use 2 transmission lines, you measure 2 different phases, and you know geometry, then you obtain epsilon E. After you measure epsilon E, can you reverse to get back to epsilon R? Definitely not, because for this equation, it's complicated, and you use these two to how to use solve epsilon R when you find epsilon E. It's impossible, right? So another scientist give you the solution. If you have epsilon r and the epsilon r is less than 1 to 8, I don't think you have the epsilon r, you will measure material more than 1 to 8. You can directly use this equation. You put an epsilon e, you find epsilon r. Okay, this is also the reverse equation for the complex epsilon e to epsilon r. This is kind of a reverse equation. Like the z0 is a reverse. You put, okay, the beginning is here. You find geometry. U, what is U? U is the ratio of W and D, okay? And you put a number of epsilon r. I think this is the initial number of epsilon r at the beginning, because you are trying to solve epsilon r, right? And then you also have the epsilon r equation. Okay? You have an initial number of epsilon r here. Or this is kind of, you need to solve the equation from another numerical tools. You put epsilon r, you put mu in these two equations, you obtain A and the B, and you have a U, then you will have a small function of F here, and then put a small function of here inside, and also another function of T. What is T? T is, this is small d, sorry, this is another d. T is the width, the thickness, another width, the thickness of the upper conductor. T. So we didn't mention that so far. So C is a function relevant to the thickness of the signal line. And this, I think this is a small d. We look at this equation just for fun. Don't worry about that. I will not ask this too crude. No one can get me a right answer. Too complicated. You need a MATLAB to solve this one. For this one, this we will leave the form of this one to another class. You use the K tool to solve the equations. Okay. Okay. This is how we get epsilon r from epsilon e. Yeah, this is I think this is, I also have a question from here as well. Maybe you need to solve that simultaneously, or maybe you put an initial number epsilon r here to get a more accurate epsilon r from epsilon. I think maybe this is epsilon r for a very low frequency, I don't know. Okay, so for this part, we are going to a very professional way to introduce the microstrip line. A lot of the numerical method, you have to use your CAD tool. The calculators, I think it is possible, I will ask you question in the final to use this until page 15 for these equations. But after page 15, you need a tool, I think. Less than 15 is possible. I will ask you for a simple result. Okay, maybe I will give you some dimension you are used to use in your project, the width and the thickness and the FR4, and you calculate what is the Z0 for that. For those numbers you're familiar with, you can check the result you are using every day. Okay? Okay, let's take a break. Small break. And it's the end of microstrip line.